Good morning, students. So this is the third lecture of chapter 9, and today we are going to cover section 9.2, which is regarding composite bodies. Okay, so let's talk about composite bodies first. What are composite bodies? So as you can see on the left side of the screen, the I-beam and the T-beam shown here. So they are commonly used in building various types of structures, right? And these are perfect examples of composite bodies because they are composed of different simple shapes like this. If you talk about this guy, which is the I-beam, so this is composed of this rectangular part, this is another rectangular part, this is another rectangular part, right? So these three rectangular parts, once combined together, so they make this I-beam, which is a composite body. Okay, and same thing about this T-beam. So this is a rectangular part, this is also a rectangular part. Once they are joined together in this fashion, then they make this T-beam. So both of these are excellent examples of composite bodies. Okay, so when doing stress or deflection analysis for a beam, the location of its centroid is very important, right? So we need to find out what is the location of centroid for a composite body. In case of this I-beam, we need to know where is the centroid of this I-beam. For this T-beam, again, we need to know, we want to know about the centroid of this T-beam, right? So that's what we are going to cover in this lecture. Okay, so just an application of the concept of centroid of a composite body. On the left side of the screen, you can see a compressor which is assembled with many individual components, right? So it has instrument panel, filter system, piping assembly, liquid storage, structural framework. So any compressor or any engine or any mechanical system is composed of different parts, right? Different components having different weights, different sizes, right? So we want to find out the centroid or center of gravity of any such system, right? So for structure analysis, it is important to determine the location of compressor's center of gravity. We call it CG, right? Center of gravity. So we want to find out the center of gravity so that we are sure that, okay, at this point, this is the center of gravity, and at this point, the whole weight of the body is acting. Okay? All right. So let's talk about the center of gravity or center of mass of a composite body. Okay. So now, to derive the equations, let's consider a composite body which consists of a series of bodies as shown in the figure, right? So let's talk about this figure, right? So we have x-axis, y-axis, z-axis. So this is important, because for any problem in mechanics, we need to define our x, y, z axis, right? Because only then we can go ahead and analyze the problem. Okay, now this composite body, let's assume that it consists of different individual bodies, right, or different individual parts having their own weights, right? So let's suppose that we have W1, W2, W3, W4 up to Wn, right? So there are infinite number of parts of this whole body, right? So individual parts, they have their own weights, W1, W2, W3 up to Wn. Okay, so now what is the resultant weight or net weight of this whole body? So we can denote this by WR, right, which is the summation of all the weights of all the individual parts or all the individual bodies, right? So WR equals summation of W, sigma W. Okay, so once we sum up all the individual weights of all the parts, then we get the resultant weight of the whole body, okay, or the composite body. Okay, now summing the moments about the y-axis, we get this equation, right? So now what is this equation, or what this equation tells us? So it gives us the moments about the y-axis. So now this is our y-axis, right? So this is our y-axis, Now we are taking the moments of all these individual weights and the total weight about y-axis, right? So the moment arm will be x bar, x1 bar, x2 bar, and x up to xn bar, right? So these are the moment arms of all these individual weights. And this x bar, this is the moment arm of the resultant weight. So x bar times WR, this is the total moment of the resultant weight about y-axis equals x1 times W1 plus x2 bar times W2 bar. It goes on till xn bar times Wn, right? So all these the moments of all these individual components. If we sum up these moments, it equals the moment of the resultant weight, right? So this is the equation which we get once we sum up the moments about the y-axis. Okay, so now in the similar way, we can sum up the moments about x and z axis to find out the coordinates of the center of gravity, right? So how do we find center of gravity? So from the earlier equation, this equation, let's call it equation 1. So from equation 1, we can get this guy. X bar equals summation of x bar times W divided by sigma W, which is the resultant weight, right? WR. Okay. So in this way, we can get the coordinate, x coordinate of the centroid or the center of gravity of the whole composite body. And similarly, we can get an equation for y bar and similarly for z bar. So once we do this analysis and we get the values of x bar, y bar, z bar of the whole body, then we can locate the centroid or the center of gravity or center of mass of that composite body. Okay, so that's how we analyze the composite body by dividing that composite body into its individual parts, right? Okay. Now by replacing the W with a M in these equations, the coordinates of the center of mass can be found. So we already discussed about that we can use these same equations of x bar, y bar, and z bar in terms of center of gravity with the once we talk about the weight of individual components and center of mass once we replace this W with mass. Okay. All right. So let's move forward and let's see these two examples, right? So these are two composite bodies, right? At the top of the screen, you can see on the left side we have a composite body. On the right side, we have another composite body. Okay, so these are made of individual simple shapes. Like this is a triangle. This is a triangle. Then we can take this part B as a rectangle or a square, and then we have this semicircle. This shape A is a semicircle, and this D is a hole, right? And whenever we analyze such kind of shape, then we take the negative area of or negative volume or negative mass of this of any hole which is there in the system or in the body. Okay. Now, if you talk about this system or this composite body, it also has different components, right? So let's talk about this guy A. So this is your rectangle, let's call it A, right? Then you can also have this triangle as E, this rectangle as D, this rectangle as C, and this triangle as B. So we can divide this whole composite body into different shapes, and we know the centroids or the x, y, and z coordinates of the centroid or center of gravity of these simple shapes, right? So we can use those numbers, we can use those values to find out the centroid or center of gravity or center of mass of this whole composite body, right? So many industrial objects are composite bodies made up of a series of connected simple shaped parts like a rectangle, triangle, and semicircle or holes, right? So we already talked about this. Okay. Now, knowing the location of the centroid or the center of gravity of the simple shaped parts, we can determine the location of the centroid or center of gravity for the more complex composite bodies, right? So we already discussed about this. Okay, now what are the steps for analysis for finding out the centroid or center of gravity of the composite body? Divide the body into pieces that are known shapes, known simple shapes, right? So we already discussed about this. Holes are considered as pieces with negative weight or negative size or negative area. So we already know this, right? Okay. So then make a table with the first column for segment number or part number, the second column for weight, mass, or size, depending on the problem. If you are going for center of gravity or center of mass or the centroid, right? So we'll use the second column for weight, mass, or size or area, right? The next set of columns for moment arms, and finally several columns for recording results of simple intermediate calculations, right? So once we go through the practice problems, so we will understand more about this step, okay? Fix the coordinate axes, determine the coordinates of the center of gravity of the centroid of each part or each piece, right? And then just fill in the table, right? So if once we do that, then sum up the columns to get x bar, y bar, and z bar. We can use these formulas, these equations, to find out x bar, y bar, or z bar, right? X bar equals summation of xi bar times ai divided by summation of ai, right? If we are talking about the centroid of the area. If we are talking about the center of gravity, then we can use this equation, x bar equals summation of xi bar times wi divided by summation of wi, right? Which is the resultant weight of all the components or all the parts, right? So these are the steps which we can use to analyze such problems. Okay, all right. So with this, we come to the practice problems. So problem 1 is shown on the screen. So you can see this shape. This is the given shape, right? And there are 3 blocks which are assembled together to make this composite body, right? And we need to determine the center of volume of this assembly, right? So as we discussed, we can find out center of gravity, we can find out center of the area, center of the volume, center of mass, anything, right? In these terms, okay? So if we can see that in this composite body, we can divide this into 3 parts, right? This is, let's say, part 1, this is part 2, this is part 3, okay? So these 3 are simple shapes. 1 and 3 are triangular shapes, and part 2 is the rectangular shape, right? So we can divide this composite body into 3 simple shapes, and then we can make the fill in the table, which we saw earlier, and then we can find out the center of volume of this composite body. Okay, so let's see how we do that. Okay, so let's give these some numbers. Let's call them A, B, and C. These 3 different parts, block A, B, and C, can be considered as 3 pieces or 3 segments. Okay, all right, so let's move forward. Now we have these three different parts of this composite body, right? They have their own dimensions, they have their own volumes. So now we can find out the volumes of each part, right? Part A, part B, and part C. So let's talk about this. Volume of part A. What is the volume of part A, right? So part A is this one, right? And this is a volume element, right? So we can just do length time width time thickness to get the volume of this part, right? So 0.5 is the thickness, 1.5 is the base, and 1.8 meters is the height. Okay, so that's how we can get the volume of this part A, right? So that's how we get the volume of this part, which is 0.675 cubic meters. Okay, Now, part B is a rectangle, right? So now part B is from here till here. This part, this is your part B, okay? So let's take the volume of this part. So again, length time width time height or thickness. So 2.5 times 1.8 times 0.5, we get the volume, which is 2.25 cubic meters, right? So this is the volume of this part, part B, okay? Now we come to part C. Now this is your part C, right? This is your part C, okay? This is a triangular element, triangular volume element, right? So again, the area of the triangle times thickness, which will give us the volume of this triangular element or part C, okay? So V sub C, this guy equals, this is the area times the thickness, so you'll get 0.675 cubic meters as the volume of this part C, okay? So now we have the volumes of each of the parts. So now we can use this table to get to the solution, okay? So first column is the part number or the segment number, right? So we have part A, part B, part C, and the summation or sigma, okay? Next, we have the volume in cubic meters, right? So just put in the numbers here, 0.675 for part A, 2.25 cubic meters for part B, 0.675 cubic meters for part C, right? We already found out, okay? So just put in these numbers and find out the total volume of this composite body, okay? Now, next thing is to find out the X, Y, and Z coordinates of the center of volume of each part. Now, just remember that we are going to take every dimension from the origin, right? So the origin is where X, Y, and Z axis meet up, okay? So if you look at the diagram, the origin is on the back side of this, so we cannot see it directly, right? But we can visualize that where X, Y, and Z axis are meeting, so that's the point of intersection of X, Y, and Z axis. That is the origin, right? So we need to take the dimensions from the origin, okay? Now for X bar, for part A, now let's talk about part A, right? So let's talk about part A, X bar, Y bar, and Z bar. So X bar is 1 meter, right? Why? Because from the origin, the X coordinate will be 0.5 meters plus 0.5 meters. So it will be 1 meters from the origin, okay? Then Y bar, so Y bar would be 0.25 meters from the origin, right? Because the thickness is 0.5 meters, which is towards y-axis, so half of it will be 0.25 meters, okay? Then once we talk about z-axis, so let's talk about z bar of part A, z coordinate of part A. So z coordinate would be from the origin, it would be 1/3 of the dimension, so 1/3 of the height, so which would be 1/3 of 1.8 meters, so we get 0.6 meters, okay? Now we are done with part A, X bar, Y bar, and Z bar, okay? All right, so now let's talk about X bar, Y bar, and Z bar for part B, okay? Again, we are taking everything from the origin, okay? So what is the X coordinate of part B, right? So X coordinate of part B would be 0.25 meters, right? You can just visualize from the given diagram. Then what is Y bar? Y bar of part B. So Y bar would be right in the center, right? Center of the part B, so which would be 1.25 meters, okay? So we get Y bar. And what is Z bar? Z bar is also in the center, so 1.8 divided by 2, so we get 0.9 meters at Z bar of part B, okay? So now we are done with part B. Now let's focus ourselves on part C. Okay, so let's talk about part C. Again, X bar for part C would be taken from the origin, right? So on the x-axis, it would be 1/2 of the thickness. So 1/2 of 0.5 meters. So we get 0.25 meters. Okay. Now along y-axis, what is the y bar? So y bar would be somewhere here, right? Somewhere here. So we need to add 2.5 meters plus this guy. So this guy is 1/3 of 1.5 meters, which will be 0.5 meters. So 0.5 plus 2.5. So we get 3 meters for y bar. Now z bar is 1/3 of the height. So 1/3 of 1.8 meters will give us 0.6 meters. Okay. So that's how we are done with these 3 columns, X bar, Y bar, and Z bar for 3 different parts, A, B, and C of this composite body. Okay. So next part, you just need to multiply X bar with volume, Y bar with volume, and Z bar with volume, right? So to get these, X bar times volume, Y bar times volume, and Z bar times volume. And everything will be meter to the 4. Okay. All right. So just simple multiplication, you get these numbers from here to here and here to here. Okay. So you get all these numbers. Okay. After getting all these numbers, we'll just sum up all these columns. Okay. So if you sum up X bar times volume, you get this. Y bar times volume, you get 5.007. Z bar times volume, you get 2.835. Okay. All right. So now let's go to the next slide and see how we utilize this summary. Okay. So now from the previous slide, we have the total volume, 3.6 cubic meters. We have X bar times volume, Y bar times volume, and Z bar times volume, right? And this is the summation. So this is the summation. All right. So now we have this. Now we can just apply, 3 different equations to get X bar, Y bar, and Z bar of the whole composite body. Okay. So let's talk about this X bar of the whole composite body. So X bar equals summation of X bar times volume divided by summation of volume. So we need to use this equation to find out X bar. So just put in the numbers, 1.406 divided by 3.6, which is the total volume, we get 0.391 as the X bar of the whole composite body. And similarly, we can use the same equation for Y bar by using this summation of Y bar times volume divided by summation of volume or the total volume. So just put in the numbers, 5.007 divided by 3.6. Right, so we get 1.39 meter, which is the Y bar of the whole composite body. And similarly, for Z bar, we use this equation, right? And we use these numbers to find out 0.788 meters as the Z coordinate of the center of volume of this whole composite body. Okay, so that's how we are done with this problem, and we found out the X bar, Y bar, and Z bar, X, Y, and Z coordinates of the center of volume of this composite body. Okay, so we are done with this problem. Now let's move over to problem 2. Okay, so now this problem, we have this composite body consisting of these different simple shapes, right? As you can see on the left side of the screen, and we need to find the centroid of this whole composite body. Okay, now we need to follow the same steps for the analysis which we saw earlier, right? Now let's talk about this shape first. So we can, first thing is to divide this shape into different parts, right? Let's divide this shape into different parts. So let's say this is a triangle. So The good thing is that this is a 2D problem, so we only have x and y axis, right? So there's no z axis. Okay, so we have a triangular part, let's call it part A. Part B is a square part. Then we have part C, which is a quarter circle. And then we have this hole, right? This hole, which is part D, which is a semicircle, right? So we have these four parts of this body, okay, of this shape. All right. So this body can be divided into the following pieces or following parts: triangle A, rectangle B, quarter circle C, and semicircle D, right? But we need to use the negative sign for the whole, right? So that's why we have plus signs between these three, this, right? So we need to add these three, and then we have to subtract this semicircle area, right, of area or part D. Okay. All right. So we are done with the dividing this shape into different simple shapes, right? So now let's move forward. Let's move forward and find out the center of area or the centroid. Okay. So now create and complete the table using parts A, B, C, and D. And again, we need to remember the XY axis and the origin, right? So this is the origin, right? This is the origin where XY axis intersect. So we need to take all the dimensions of X bar, Y bar from the origin. Okay. Now let's have a look at this table. Okay. So first column is the segment, as we did in problem 1. Okay. So we have 4 different parts. So we have a triangle A, we have a rectangle B, we have a quarter circle C, and we have a semicircle D. And then we have the last 4 for the summation. Okay. All right. So now in last problem, we were talking about the volume, center of volume. Now we are talking about, in this problem, we are talking about the center of area or the centroid, right? So let's talk about the area. So we are talking about the area in inch square because all the dimensions are in inches. So area would be in inch square. So first of all, let's talk about triangle. Okay, triangle A. So what is the area of the triangle? We know it's 1/2 times base times height. So 1/2 times 3 inches times 3 inches, which is the height, right? So it would be 4.5 inch square. Okay. Now let's talk about the X bar. X bar of this part A, which would be in inches, right? So we want to take everything from the origin. From the origin, the X bar would be somewhere here of part A, right? Which would be one third of the base. So 1/3 of 3 inches would be 1 inch, right? So this guy is 1 inch, right? So 1 inch plus 3 inch from the origin, so it would be 4 inches. But it's on the negative X, it's in the negative X direction, so it'll be a -4, right? So let's take it as -4. Now let's talk about Y bar. Y bar of this part A, right? So Y bar would be somewhere here, right? So somewhere here, which would be 1/3 of the height, right? So 1/3 of 3 inches again, so which would be 1 inch, right? So if we take it from the origin, so 1 inch, 1 inch upward, right? In the upward direction or positive Y direction, so it will be +1. So we have a +1 for Y bar of part A. Okay. Now let's talk about the part B, which is the rectangle, right? So now we are talking about this guy, this part B. Okay. So let's talk about this part B. Okay. Now what is the area? You know that it's base times height. So 3 times 3, we get 9 inch square as the area of this part B. Okay. Now what is the X bar? X bar of this part B. So X bar, we know that it will be in the center of this rectangle on the X-axis, right? So again, it's in the negative x direction, so it'll be a negative 1.5 inches. So negative 1.5 inches as x bar. Okay. Then we want to find out the y bar. So y bar would be somewhere here, right? So y bar would be somewhere here, which is again, which would be in the center, right? So 1/2 of 3 inches, so it'll be 1.5 inches, but as it is in the positive y direction, so it'll be a positive 1.5. Okay, so 1.5 inches. Now let's talk about this quarter circle C. Okay, quarter circle, which is this guy, right? This guy. This is your quarter circle. Okay, so what is the first of all the area of this quarter circle, right? So we know that area of the circle is pi r square. Okay, so what is the area of quarter circle, or let's say a sub c? It's pi r square divided by 4, right? And what is the radius? Radius is 3 inches, so 9 pi by 4, right? So we get this as the area of this quarter circle, 9 pi by 4. Now what is the x bar? X bar, so let's talk about x bar, right? So x bar of quarter circle, x bar would be 4r over 3 pi, right? And similarly, we have same for y bar. Okay, so this is 4r over 3 pi is the equation which we can use to find out the center of area for these quarter circle and semicircle. Okay, all right, so if we use this formula, 4 times r divided by 3 times pi, we can come here, right? 4 times 3, which is the radius, divided by 3 times pi, so that's how we get x bar. And same thing for y bar, 4 times r, which is the radius, which is 3 inches, divided by 3 times pi. So that is the x bar and y bar of this quarter circle. Okay, all right, from the origin. Okay, now let's talk about this semicircle or part D. Okay, this guy. So we are talking about this guy. So this is your part D. All right, let's call it here. This is your part D. Okay, let's talk about this part D. So this is a semicircle. Okay, now what is the area? We know that area is pi r square, right? So pi r square is for full circle. So for semicircle, it will be pi r square times 1/2, right? So 1/2 times pi r square. Radius is 1 inch, right? So 1 inch radius will give us negative pi by 2, right? This is the area because this is a hole, so that's why we use this negative sign, right? So the area is pi by 2, and we are using this negative sign to show this whole area, okay? Area of the hole, okay? All right, now what is the x bar? X bar, now we know that x bar is at this point, right? Right at the origin. So that's why we don't have the value for x bar or x bar equals 0. Now what is y bar? Y bar is again 4r over 3 pi. So r is 1 inch. So we get 4 times 1 divided by 3 times pi as the y bar of this part D, right? So now we are done with these first 4 columns, talking about the segment, the area of each part, the x bar and y bar of each part. Okay, now let's talk about the next 2 columns, which are just the multiples of the initial columns. So x bar times area and y bar times area will give us these values, these numbers. Okay, so these numbers, so just simple multiplication, so let's not go into the details. Okay, so after doing that, let's talk about this next row, which is the summation of area and summation of the last 2 columns. Okay, so just sum up all the areas of different parts to get the area of the whole composite body. Okay, so which will be 19 inch square, which is the area of the whole composite body. Okay, and sum up x bar times area of all the parts, so we get negative 22.5, okay, inch cube. And y bar times area, so we get 26.33 inch cube, right? So that's how we are done with this table. Now let's go on to the next slide and let's see how to use these this summary. Okay, so now we got to this point. We got summation of area, which is 19 inch square. We got summation of x bar times area, which is negative 22.5 inch cube, and we got summation of y bar times area of all the four parts, which was 26.33 inch cube, right? Now just use simple equations. X bar equals summation of x bar times area divided by summation of area, right? This guy. Just put in the values. What do we have? Negative 22.5 inch cube divided by 19 inch square, right? So we get this guy, negative 1.18 inches as our x bar, right? Now, similarly for y bar, this is how we calculate y bar. So y bar equals summation of y bar times area divided by summation of area, okay? You just use these numbers, 26.33 inch cube divided by 19 inch square, right? So we get this number, which is 1.39 inches, which is the y bar of the whole shape, okay? So that's how we are done with this problem, and we wanted to find out the centroid of the whole shape. So we followed these steps, and finally we came to this point where we have the values of x bar and y bar of the whole shape. All right. Okay. Now, last thing, we want to see where this centroid is, right? So just locate the centroid with respect to the origin. So this is our origin, right? So what is the value of x bar is negative 1.18 inches. So on the negative y-axis, let's say somewhere here, right? Let's say somewhere here. This is your x bar. This is your x bar. Okay. Now y bar is 1.39 inches, right? So let's say somewhere here. Okay. Somewhere here. So this guy is your y bar. Okay. So now if you locate these x bar and y bar to a point, let's say this is the point which we can call capital C, or the centroid of the whole shape, right? Now, after doing this analysis, we can just visualize that this point C, or the centroid of the shape, looks correct. So, I mean, looking at this whole shape or whole area of this composite body, we can say that, okay, this centroid looks right. Okay, but let's say if we get some solution where we get the centroid somewhere here, right? Let's call it C1. Okay, so let's say if we get a centroid somewhere here, then it seems incorrect, right? Because we cannot have the centroid of the body on one side. It has to be somewhere in the center, right? So the point C looks to be in the center, but point C1 doesn't seem to be in the center, right? So if we get something like C1 as the centroid, then we can say that, okay, there is something wrong within our solution, right? Maybe some multiplication error or some formula error or something, right? So that's why we are not getting the correct answer. But if we get something like this, then we can say, okay, it seems right. Okay, so that's how we are done with this problem, finding out the centroid of this complex shape by following these steps and filling out this table and applying these equations. We can find out x bar and y bar of the centroid of this complex shape. All right. Okay, so with this, we come to the end of this lecture, and we come to end of chapter 9. All right. Thank you.